Tonight, the moon is up there. You might not be able to see it right now. It might be behind clouds, or on the other side of the sky, or in a phase too thin to notice. But it's there. It has been there every single night of your life, every night of every human life, every night since before our species existed. But what if you woke up tomorrow and it was gone? Not dimmer, not further away. Gone, vanished, the sky completely empty where it used to be. The tides would change within hours. The nights would become darker than anything alive today has ever experienced. Within months, Earth's axial tilt would begin to destabilize. Within thousands of years, the planet's seasons would become unrecognizable, and the oceans, the weather, the length of your day, the very stability of the climate that allowed civilization to exist, all of it connected in ways most people never think about, to that pale circle in the night sky. Tonight, we follow what happens. From the first moonless night to the far future of a world that forgot it ever had one. Let's begin. Before we explore what a moonless world looks like, it helps to understand what the moon is actually doing right now. Most people think of the moon as a light source, something pretty to look at, something that affects the tides in a vague, general way, maybe something romantic. But the moon is, in reality, one of the most important stabilizing forces in Earth's history. Its effects touch almost every system on the planet, and most of those effects are invisible in daily life. You only notice them when you start to think about what would happen without them. The moon formed about 4.5 billion years ago, very shortly after Earth itself. The leading scientific theory is called the giant impact hypothesis. A Mars-sized body, which scientists call Theia, collided with the early Earth at an angle. The collision was enormous, not a head-on crash, but a glancing blow that tore material from both bodies. That material was ejected into orbit around Earth, and over time, it coalesced into the moon. This origin story matters because it means the moon started out much, much closer to Earth than it is today. Just after formation, the moon was perhaps 20 to 30 times closer. Earth's days were only a few hours long. The tides raised by the nearby moon were hundreds of meters high, washing over continents twice a day. Since then, the moon has been slowly moving away. Every year, it retreats about 3.8 centimeters from Earth. The tides, by transferring rotational energy from Earth to the moon, have been gradually slowing Earth's rotation and pushing the moon outward. It's a slow process, imperceptible in a human lifetime, but relentless. Right now, the moon sits about 384,000 kilometers away, far enough that it looks small in the sky, but close enough to exert a profound gravitational influence on our planet. That influence shows up in three main ways: the tides, Earth's axial stability, and the length of our day. And all three are about to change. The moon disappears. The first thing you notice is the darkness. We have forgotten what genuine darkness looks like. Even on a new moon night, when the moon is between Earth and the sun, showing us only its dark side. There is still reflected light from stars, from the Milky Way, from the distant glow of cities. We live in a world saturated with artificial light, and most of us have never experienced true darkness. But even for people far from cities, even in the darkest wilderness on Earth, the moon provides something. On a full moon night, the surface of the moon reflects enough sunlight to cast shadows. You can read by moonlight if you hold the page at the right angle. Animals navigate by it, predators hunt by it, prey species hide from it. Without the moon, the night sky becomes something different. The stars are still there. In fact, with no lunar glare washing out the sky, you would see more stars than you ever have before. The Milky Way would be visible in a way it almost never is from populated areas. The sky would be extraordinarily beautiful, but it would be completely, utterly dark at ground level. This matters immediately for nocturnal life. Every species that uses moonlight to navigate, hunt, or avoid predators would have its behavior disrupted overnight. Literally overnight. Sea turtles, which navigate to nesting beaches by the glow of the moon on water, would lose one of their primary orientation cues. Dung beetles, which use the Milky Way and moonlight to navigate in straight lines across the savanna, would be disoriented. Migratory birds that fly at night use the moon as a compass. Some species use it in combination with star patterns and magnetic fields, but removing one of those reference points affects their navigation accuracy. Predators that hunt by moonlight, owls, certain cats, many small carnivores, would have an advantage in the newly dark nights. Prey species that currently use moonlight to spot approaching predators would be more vulnerable. These shifts in behavior would cascade through ecosystems. Some prey populations would decline, some predator populations would grow. Scavengers and species that prefer darkness would expand into niches previously held by moonlight-dependent animals. But this is just the first night. The ecological disruption from darkness alone is manageable. What comes next is more significant. Within hours of the moon's disappearance, the tides begin to change. Currently, Earth has tides because the moon's gravity pulls on the ocean. The side of Earth facing the moon experiences a stronger gravitational pull than the center of the Earth, and the center experiences a stronger pull than the far side. This differential pull, called the tidal force, stretches the oceans slightly toward and away from the moon. The result is two bulges of water, one on the side facing the moon and one on the opposite side. As Earth rotates, these bulges sweep across the ocean basins, creating the familiar rhythm of high and low tides. Without the moon, these bulges disappear. Tides don't vanish entirely. The sun also exerts a tidal force on Earth, smaller than the moon's, because distance matters more than mass for tidal forces, and the sun is much farther away than it is massive. Solar tides are about 46% the strength of lunar tides, so without the moon, tides would still exist. But they would be less than half as strong, and and they would follow the sun's position rather than the moon's. This sounds like a minor adjustment, but it has profound consequences. Tidal mixing is one of the ocean's most important processes. When tidal currents flow over shallow sea floors, over underwater ridges and seamounts, they create turbulence that mixes the ocean vertically. This mixing brings cold, nutrient-rich water from the deep up to the surface, where sunlight can power photosynthesis. It distributes heat, it circulates the chemicals that marine life depends on. Weaker tides mean weaker mixing, less nutrient upwelling, lower productivity in coastal zones and shallow seas. These coastal and shallow water ecosystems, the continental shelves, the estuaries, the tidal flat zones, are among the most productive environments on Earth. They support enormous fisheries. They nurture the juvenile stages of many open ocean species. They filter pollutants before they reach deeper water. With weaker tides, these zones change character. Estuaries, which depend on tidal flushing to circulate fresh and salt water, become more stagnant. Tidal flats, which are exposed and submerged on regular schedules that the organisms living there depend on, become irregular. Species adapted to a specific tidal range would need to adapt to a different one. There is something else. Tidal forces from the moon are also responsible over geological time for the slow drift of Earth's tectonic plates, or at least they contribute to it. The moon's gravity acts as a subtle but constant force on the fluid mantle beneath the Earth's crust. Over millions of years, this contributes to the movement of plates. Without it, plate tectonics would continue. It is driven primarily by heat from the Earth's interior, but the patterns might shift subtly over geological timescales. But these geological changes are far in the future. The more immediate effect of weakened tides is on life in the coastal ocean, and the changes begin within days. Here is something that surprises most people. The moon is currently slowing Earth's rotation. The tidal bulge that the moon raises in the ocean doesn't line up perfectly with the moon's position. Earth rotates faster than the moon orbits, so the tidal bulge is always slightly ahead of the moon in Earth's rotation. The moon's gravity pulls backward on this bulge, creating a very small but constant braking force on Earth's spin. Over geological time, this has added up enormously. When the moon first formed, Earth's day was about 6 hours long. Today, it's 24 hours. The moon has been gradually lengthening our day for 4.5 billion years. Without the moon, this braking force disappears. Earth's rotation would still slow down over time. The sun also exerts a small tidal braking force, but much more slowly. Left without the moon, Earth's day would stabilize at something significantly shorter than it currently is. Or rather, it would continue lengthening, but at a much slower rate. This sounds abstract, but it has practical consequences. Day length affects climate. Shorter days mean faster cycling of heating and cooling at the surface. Longer days, which is what we're heading toward naturally, mean more extreme temperature differences between daytime highs and nighttime lows. The current 24-hour day is long enough to develop significant weather systems, but short enough that temperature extremes stay within ranges most life can tolerate. A world with significantly different day length would have different weather patterns, different temperature ranges, different growing seasons. Without the moon's breaking, Earth might not have settled into the exact 24-hour rhythm it currently has. The length of our day and all the climate patterns built around it is partly a product of the moon's long gravitational influence, but this is a slow effect. On human timescales, the day length change from removing the moon would be imperceptible for millions of years. Something else happens much faster. This is where things become genuinely strange. Earth's axis is currently tilted at about 23.5 degrees relative to its orbit around the Sun. This tilt is why we have seasons. When the northern hemisphere is tilted toward the Sun, it receives more direct sunlight, more hours of daylight, and experiences summer. When it's tilted away, it receives less, winter. The tilt of 23.5 degrees is not fixed. It varies. Over a cycle of about 41,000 years, Earth's axial tilt wobbles between about 22 degrees and 24.5 degrees. This slow wobble is called obliquity variation, and it is one of the factors, along with orbital shape changes and the precession of the equinoxes, that drives the long ice age cycles on Earth. What keeps this variation relatively small, between 22 and 24.5 degrees, is the moon. The moon's gravitational influence stabilizes Earth's axial tilt. It acts as a kind of gyroscopic anchor, preventing the tilt from drifting too far in either direction. Without the moon, computer models suggest that Earth's axial tilt could vary wildly, anywhere from near 0 degrees to perhaps 85 degrees, over timescales of millions to tens of millions of years. The consequences of this would be extraordinary. At near zero tilt, Earth would have almost no seasons. The equator would be permanently hot, the poles permanently cold, and the middle latitudes would experience very mild, uniform conditions year-round. Many species that depend on seasonal cues for reproduction, migration, or hibernation would struggle to adapt. At very high tilt, say 60 or 70 degrees, the seasons would be extreme. The poles would receive more direct sunlight than the equator during summer. In polar summer, the sun would be almost directly overhead at the poles for months. In polar winter, the poles would be in total darkness for months, and they would become the coldest places on Earth. The tropics, meanwhile, would have seasons of their own, months where the sun barely climbs above the horizon. The climate patterns we know, the distribution of deserts, forests, grasslands, and tundra across different latitudes would be completely different at high axial tilt. The locations where agriculture is possible would change dramatically. Precipitation patterns would shift. Species would need to migrate, adapt, or go extinct. This tilt destabilization doesn't happen overnight. It would take millions of years to fully develop. But it is perhaps the most significant long-term consequence of losing the moon. We live on a planet with stable, predictable seasons, partly because the moon is up there, quietly holding our axis in place. As the axial tilt begins its slow drift, the oceans would respond. Ocean circulation is driven by several forces: temperature differences, salinity differences, wind patterns, and, less obviously, the rotation of the Earth and the tidal mixing we discussed earlier. All of these would be subtly affected by the moon's absence. In the short term, the most noticeable change is in the coastal zones. Without strong tidal mixing, upwelling of deep ocean nutrients weakens in many areas. Fisheries that depend on this upwelling productivity, the great fishing grounds off the coasts of Peru, Namibia, California, and elsewhere, would become less productive. Marine food webs are built on phytoplankton, the tiny photosynthetic organisms that form the base of almost all ocean life. Phytoplankton needs sunlight and nutrients. Sunlight they have, but many of their nutrients, nitrogen, phosphorus, iron, come from deep water brought to the surface by mixing. Less mixing means less nutrients, means less phytoplankton, means less of everything above them in the food web. Fish populations would decline in many areas, not immediately, not dramatically, but steadily over decades and centuries, as the productivity of coastal ecosystems slowly weakens. Over longer timescales, as the axial tilt begins to drift, ocean circulation would be further disrupted. The great conveyor belt of deep ocean circulation, which moves cold, dense water from the poles to the tropics along the sea floor, and warm surface water back to the poles, depends on temperature and salinity gradients that are themselves products of the current climate. As the climate changes with a wandering axial tilt, these gradients change. The conveyor belt shifts. Ocean heat distribution changes. The regions that are currently warmed by ocean currents, like northwestern Europe, which is much warmer than its latitude would suggest because of the Gulf Stream, would experience different temperature regimes. The ocean is not just a body of water, it is a climate regulator, a food source, a carbon sink. Everything that changes in the ocean affects the atmosphere, the land, and the life that depends on both. Through all of this, the darker nights, the weakened tides, the slowly wandering axial tilt, the changing ocean productivity, life would be adapting. This is what life does. It has been adapting to changing conditions for billions of years. Ice ages, asteroid impacts, volcanic winters, mass extinctions. Life has survived all of them, not unchanged, but surviving. The question is not whether life would survive the loss of the moon. It would, but what kind of life? Species with short generation times adapt fastest: bacteria, insects, small rodents. They can produce new generations quickly enough that natural selection has material to work with on timescales of centuries or millennia. If a new ecological niche opens up Because of the changed tidal regime, there will likely be something that evolves to fill it within a few thousand years. Larger, slower reproducing species have much more trouble. A whale, which may have only one offspring per year and reaches reproductive age after a decade, cannot adapt to changing ocean conditions as quickly as a bacterium dividing every 20 minutes. The great whales, already under pressure from human activities, would face additional stress from declining ocean productivity and changing migration routes. Coral reefs, which are already among the most vulnerable ecosystems on Earth, would face new pressure from changes in tidal patterns, water chemistry, and the shifting climate that comes with axial tilt variation. Many reef systems that are currently just barely surviving might not make it through the additional disruption. Forest ecosystems would eventually need to reorganize as the axial tilt drifts and seasons change character. The species composition of forests, which is tightly tied to the seasonal patterns of temperature and precipitation, would shift. Some species would move poleward or to higher elevation as conditions change. Others would decline. Over millions of years, the forests of a world without the moon would look very different from the ones we have today. But here is something important to hold on to. None of this would be sudden. Even the loss of the moon itself, in this scenario, is instantaneous. But the consequences unfold over human timescales, geological timescales, evolutionary timescales. The Earth would not end, life would not vanish, the planet would simply change, slowly, continuously, into something different, something that had forgotten it ever had a moon. Humans are the most adaptable large mammal that has ever existed. We live in deserts, in Arctic tundra, in tropical forests, at high altitude, in places no other primate could survive. We have been doing this for tens of thousands of years, using technology and cultural knowledge to extend our range far beyond what our biology alone would allow. So yes, humans would survive the moon's disappearance, but the world would not be the same. In the short term, the main human concerns would be practical and ecological. Fisheries declining due to reduced tidal mixing would affect food security for hundreds of millions of people who depend on fish as a primary protein source. Coastal communities whose livelihoods depend on predictable tidal patterns, fishing, aquaculture, navigation, would need to adapt to the new, weaker solar tidal regime. Agriculture would eventually be affected as the axial tilt begins to drift. Farming is built around seasons. The timing of planting and harvest, the distribution of rainfall, the risk of frost, all of these depend on predictable seasonal patterns. As the tilt drifts and seasons change character over millions of years, agricultural practices would need to change with them. But the time scale for significant tilt change is so long, millions of years, that it's not a practical human concern on any foreseeable time scale. The darker nights would be, in a strange way, one of the more culturally significant changes. For most of human history, The moon has been the primary light source after dark. Every calendar system ever developed, lunar, lunisolar, solar, was built around the moon's phases. The months we use today are descended from lunar cycles. The word month comes from the same root as moon. Ramadan, Easter, Passover, Diwali, many of the world's major religious observances are tied to the lunar calendar. Without the moon, human culture would eventually lose this connection. The night sky would become something to navigate by stars alone. The 29.5-day cycle that has structured human religious, agricultural, and social life for tens of thousands of years would disappear. New cycles would develop, new calendars, new ways of organizing time. But the moon's absence would not just be cultural, it would be felt. There is something about looking up and seeing the moon that no description fully captures. Its slow movement across the sky, its phases unfolding like a slow, reliable clock. The way it illuminates a landscape at night so softly that you can walk through it without stumbling. The way it sits on the horizon at moonrise, enormous and orange, and then shrinks and whitens as it climbs. These experiences, which humans have had every night for their entire history as a species, would simply be gone. The sky would be different, darker, more star-filled, more beautiful in some ways. But something would be absent, something that every human culture has looked up at, named, wondered about, worshipped, and navigated by. The night sky without the moon would be a different kind of sky. There is a line of thinking in planetary science called the rare Earth hypothesis. It argues that the conditions required for complex life, not just microbial life, but the kind of complex, multicellular life that eventually produces creatures capable of looking up at the night sky and wondering about it, are extraordinarily rare in the universe. One of the conditions they point to is having a large moon. A large moon stabilizes the axial tilt. Stable axial tilt means stable seasons. Stable seasons mean a climate that stays within a relatively narrow range over geological time. A stable climate, the argument goes, allows ecosystems to develop the complexity and continuity needed to eventually produce intelligence. Mars has two small moons, Phobos and Deimos, too small to stabilize its axial tilt. Mars's tilt varies between 15 and 35 degrees over millions of years, a much wider range than Earth's. Over geological time, Mars has experienced climate swings far more extreme than Earth's, possibly contributing to the loss of its atmosphere and liquid water. Venus has no moon. Venus rotates so slowly that a Venusian day is longer than its year. Whether a moon would have made Venus habitable is debated, but the contrast with Earth is striking. Earth has the moon, and Earth has complex life. This doesn't prove the moon caused the complex life. Correlation is not causation, and there are many other factors. But it suggests that the moon is not merely a beautiful accident. It may be part of the reason we're here at all. When you look at the moon tonight, if it's visible, if the sky is clear, you're looking at something that has been holding our axis steady, regulating our tides, lengthening our days, and very possibly making complex life on this planet possible for 4.5 billion years. It formed from the debris of a catastrophic collision. It has been slowly moving away from us ever since. One day, in the very distant future, it will be too far away to fully stabilize our tilt or create solar eclipses. The moon we see tonight is not permanent. Nothing is. But right now, tonight, while you sleep, it is up there, pulling the ocean in its slow, ancient rhythm, holding the axis of the planet steady against the gravitational chaos of the solar system, making the seasons what they are, making the night what it is, and making this world, with all its specific, improbable conditions for life, exactly what it has been for the billions of years it took to get to us. Music slowly fading to silence. Good night, and if you get a chance, look up before you sleep.